Welcome to the Problemas channel Season 1 Episode 8, the episode in which we will discuss the solution of the problem S1M9. Before we do that, however, please allow me to welcome the newest members of our channel. Last week I noticed that several people whom I personally know from Quora have decided to join our channel, and for that I am both grateful and honored. Thank you very much. Because you're joining our channel mid-flight, so to speak, please allow me to explain how we do things on this channel. In Season 1, Episode 1, I gave several concise enough yet faithful enough definitions of mathematics, and in Season 1, Episode 2, I explained how to practice mathematics correctly, and in that episode I also explained a difference between a mathematical exercise and a mathematical problem, which explains why on this channel we do not do any exercises, but we only solve problems. For your viewing convenience, I have put these two episodes, Season 1 Episode 1 and Season 1 Episode 2, into a dedicated playlist called The Fundamentals. We study mathematics, theoretical physics, and computer science on this channel by solving the corresponding problems, and the way we do that is as follows. Starting with Season 1, Episode 2, at the end of the current episode, I present the next problem, and our viewers have a chance to practice mathematics correctly, as was explained in Season 1, Episode 2, and generate a solution of this or that problem completely on their own. In the next episode, I discuss one or several solutions of that problem, usually generated by me, and our viewers that way have an opportunity to compare their solution to the solution or the solutions presented on this channel. Also on this channel we try to not solve the problems haphazardly, but we try to solve problems more or less systematically by applying the so-called problem-solving approaches to the process of unlocking a solution of this or that problem. Consequently, we already solved our first 8 mathematical problems, S1M1 through S1M8, across Season 1 Episodes 3, 4, 5, 6, and 7, which again, for your viewing convenience, I have arranged into a dedicated playlist called Transform and Conquer, because in Season 1 Episode 4 I explained the mechanics of this particular problem-solving approach, and we solve these 8 mathematical problems precisely by applying the transform and conquer problem-solving approaches to unlocking a solution of these problems. In the lightning round, in these first 8 problems, we mostly dealt with regular polyhedrons, such as a regular tetrahedron, a cube, and the regular octahedron. We also discussed briefly the so-called groups of rigid symmetries of a regular dodecahedron and of a regular icosahedron. And in the problem S1M5, which was rated as very difficult with 2 asterisks, we solved an interesting problem that dealt with an orbit that circumnavigates the outer surface of a regular tetrahedron in such a way that it visits every face of that solid and is the shortest possible in length. And we proved that the corresponding cross section divides or partitions that solid into 2 equal solids, which separately look very strange. And even when these 2 solids are put together, the shape is still not really clear what it is. But the moment these 2 halves are rotated one with respect to each other, like so, as if by magic, a regular tetrahedron results. In my problem-solving career, I managed to identify 11 problem-solving approaches listed over here. Out of these 11 problem-solving approaches, across the 5 episodes shown over here, Season 1 episodes 3, 4, 5, 6, and 7, we already studied the mechanics of the so-called transform and conquer problem-solving approach. Starting with this episode, we begin the study of the problem-solving approach, to which I refer as reinterpret and conquer. I try to rep or present the mechanics of each of these problem-solving approaches in a language that is as simple as possible but not simpler, and in a language that doesn't require many years of highly specialized and dedicated training, because the pedagogical wisdom to which I was exposed says that even though, for example, in college and after college, the mathematical notions that you will be manipulating will be much more abstract and much more specialized, such as topological spaces, vector bundles, tensors, quadratic residues, field extensions, automorphism groups, kernels of homomorphisms, factor groups, normal subgroups, and so on. The mechanics of the creative process that manipulates these notions into submission remains essentially the same as the process or the creative process of manipulating the basic mathematical notions that we are dealing with into submission. As such, in the last 7 years, the questions that I have been answering on Quora came in all shapes and sizes and randomly, so to speak. But on this channel, I would like to present a coherent or a consistent view of the tools that I used in order to do what I did. In other words, my plan is to explain how each of these problem-solving approaches works individually. We will continue with this episode with the explanation of how the reinterpret and conquer problem-solving approach works. Then we will take on the remaining problem-solving approaches listed here in sequence. We will look at the reverse order problem-solving approach, the space-time problem-solving approach, the equation, the scope reduction, the scope expansion, the eliminate and conquer, the divide and conquer, the invariant, and the equivalence problem-solving approaches one by one. The idea behind this way of studying the problem-solving approaches is quite simple. If we understand how each of these problem-solving approaches works individually, then we should be able to string these approaches together into order-sensitive formations, or more pedantically, permutations of problem-solving approaches that may help us solve more and more difficult and more advanced problems, which brings us to the solution of the problem S1M9. As a reminder, in the problem S1M9, we're given a garland of 100 light bulbs. Because this garland was shipped from the manufacturer in a state in which we cannot really tell which light bulbs are on and which light bulbs are off, during the first walkthrough, our friendly dwarf, who is no doubt gunning for a bachelor's degree in mathematics, walks along the garland of light and turns every light on. Then our dwarf conducts consecutive walks along the garland of light, and on every kth walk along that garland, the dwarf flips or changes the state of each kth light bulb to its opposite, which means that if the kth light bulb is on, then the dwarf will turn it off, and if the kth light bulb is off, then the dwarf will turn it on. For example, during the second walk along the garland of lights, The dwarf will change the state of every second light bulb to its opposite. Consequently, during the third walk along the garland of lights, our dwarf will flip the state of every third light bulb, or the light bulb number 3, 6, 9, 12, 15, and so on, to its opposite. During the, let's say, seventh walk along the garland of light, our dwarf will change the state of each light bulb number 7, 14, 21, 28, 35, and so on to its opposite, and so on. And the question is, by the end the dwarf completes or finishes the 100th walk along the garland of lights, then which light bulbs will be on, shining brightly, and which lights will be off? It turns out that this problem, of course, can be solved in a so-called brute force manner, in which we basically follow in the footsteps of the dwarf, and we conduct all 100 walk-alongs the garland of light, and at the end of the 100th walk along the garland of lights, we see which lights are off, we see which lights are on, and we announce to the world that the lights numbered blah 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 are on. However, no one in the mathematical communities cares about the answer that we produce, and especially no one in the mathematical community cares about that particular type of an answer, because there is no insight, there is no interesting story behind why the light bulbs so and so are off and why the light bulbs this and that are on. Remember that first and foremost, mathematics is an art of telling a story of how and why. A little bit later on, mathematics also, or in parallel, becomes an art of telling a story of how and why, wrapped into the technical language of 3 logical connectives and not or, 2 quantifiers, existential and universal, and 1 implication, if P then Q. Later on yet, also in parallel or in addition to, mathematics becomes the study of structure divorced from any specific context. However, our initial ambition is to learn how to generate or how to construct a story of how and why attached to this or that mathematical problem. Consequently, those of our viewers who were able to solve this problem correctly and on their own perhaps went through the stage number 4 of practicing mathematics correctly and tried to generalize and abstract that problem, the solution of that problem. And the abstraction of the generated solution that our viewers obtained was or is essentially or very close to what I refer to as the Reinterpret and Conquer problem-solving approach. That approach is a close cousin of the just studied Transform and Conquer problem-solving approach, but the Reinterpret and Conquer problem-solving approach is slightly more subtle, slightly more nuanced, and slightly more delicate. The Reinterpret and Conquer problem-solving approach works in essentially the same way as the Transform and Conquer problem-solving approach, and according to the Reinterpret and Conquer problem-solving approach, we should try to find, or we should look for, a successful and fruitful candidate different interpretation or reinterpretation of the logical or local subject matter that possesses the following 2 fundamental properties. Such a reinterpretation should preserve the technical essence of the original problem, because evidently we want to solve this problem and not some other problem. And the candidate reinterpretation should allow or afford us a tactical advantage that makes the process of searching for a solution of the reinterpreted problem more straightforward or more easier in some sense. Now, how does the reinterpret and conquer problem-solving approach may be applied to the solution of this problem. In order to see how reinterpret and conquer problem-solving approach can work in this specific case, we begin with an activity that is quite popular in mathematics called an experiment. And if someone in your past travels have told you that an experiment is the sole purview of physics, chemistry, or biology, then that will be not true, because practicing or grown-up mathematicians engage in experimentation or thought experiments on the regular basis. In this case, we will limit our experimentation to 10 lights and to 10 walks along the garland of lights, as explained before. Also, I will portray the light that is on with a yellow chalk and a solid yellow circle. So on the black background, hopefully you can see that the light is on. And I will portray the state of the light bulb as off with a hollow blue circle. We are told that by the end of the first walk along the garland of lights, all the lights, which means all the light bulbs numbered 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, are on. Before we begin our second walk along, what type of actionable information can we squeeze from this unit of the problem statement? Well, we're told that during the second walk along, the dwarf will flip or change the state of every second light bulb to its opposite, which means that during the second walk along, the dwarf will act on the light bulb's number 2, 4, 6, 8, 10, 12, and so on. But what does that mean? That means that never ever again, for the duration of this problem, the dwarf will act on the light bulb number 1. And that means that the state, or the current state, of the light bulb number 1 can be carried or percolated all the way down to the end of the experiment as it is. In other words, right here, right now, we mark the state of every walk along for the light bulb number 1 as on, 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 and on. Next, we know that in this particular case, the dwarf will essentially turn off every second light bulb. In other words, the light bulb number 2 will be off, the light bulb number 4 will be off, the light bulb number 6 will be off, 8 off, 10 off. Now that we mark the states of each and every light that the dwarf acted on during the second walk along, we can carry down the states of all the lights that the dwarf did not act on, which means that the light bulb number 3 will be on, 5 on, 7 on, 9 on. Very well. Before we begin our third walk along, what kind of actionable information can we squeeze out of this particular unit of the problem statement? Well, we know that during the third walk along, the dwarf will act on the light bulbs number 3, 6, 9, 12, 15, 18, and so on, which means that never, ever, ever again, the dwarf will act or touch the light bulb number 2. And that means that the state of the light bulb number 2 can be percolated all the way down to the end of the experiment safely, like so. Off, 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 and off. Now, during the third walk along, the state of every third light must be changed to its opposite, which means that the state of the light bulb number 3 right now is on, and now it becomes off. The light bulb number 6 was off, now it goes on. The light bulb number 9 was on, now it goes off, and that completes the action on the every third light bulb, and we can carry down the states of all the light bulbs that the dwarf did not act on as is. In other words, number 4 is off, number 5 is on, number 7 is on, number 8 is off, and number 10 is off. Before we begin our fourth walk along the garland of lights, what kind of actionable information can we squeeze from this unit of the problem statement? Well, that means that the dwarf will never ever touch the light bulb number 3 along with light bulbs 1 and 2. And that means that the state of the light bulb number 3 can be percolated all the way down to the end of the experiment safely as follows: off, 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 and off over here. And during the fourth walk along, the dwarf will change the state of every fourth light bulb to its opposite, which means the light bulb number 4 goes on, the light bulb number 8 goes on, and this is it for this walk along. And that means that we carry down the states of all the remaining light bulbs that the dwarf didn't act on as is. Number 5 is on, 6 is on, 7 is on, 9 and 10 are off. Before we execute the fifth walk along the garland of light, what kind of actionable information can we squeeze from that unit of the problem statement? Correct. That means that during or after the fifth walk along, the dwarf will never touch the light bulbs number 1, 2, 3, and 4. And that means that we can carry the state, the current state of the light bulb number 4, all the way down to the end of our experiment safely as it is. So the light bulb number 4 goes on, 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 and on. And in this fifth walk along, we change the state of the light bulb number 5 to its opposite. It was on, now it's off. And the state of the light bulb number 10, 5, 10, 15, 20, 25, and so on, goes from off to on, like so. And we're done. Consequently, before the sixth walk along the garland of lights, we already see that the dwarf will never act on the light bulbs numbered 1, 2, 3, 4, and 5, which means that the state of the light bulb number 5 can be carried down to the end of the experiment safely, like so, off. And during the sixth walk along, what do we do? Oh, I'm sorry, I forgot to carry down the states from the previous walk along. 6 is on, 7 is on, 8 is on, and 9 is off. So during the sixth walk along, the dwarf will act on the light bulb number 6, and right now that light bulb is in the on state. Consequently, the dwarf will turn it off, and then it will act on the light bulb number 12, 18, 24, 30, 36, and so on. But that means also that we carry down the states of the light bulbs that the dwarf did not act on as is. In other words, 7 is on, 8 is on, and 10 is on, but 9 is off, like so. Before the seventh walk along, we understand that the dwarf will never act on the light bulbs 1, 2, 3, 4, 5, and 6, which means that we can carry down the state of the light bulb number 6 all the way to the end of the experiment safely. During the seventh walk along, the dwarf will act only in our experiment light bulb number 7. It was in the state on. The dwarf will turn it off, and we bring down or percolate down the states of the light bulbs that the dwarf did not act on, like so. 8 is on, 10 is on, and 9 is off. Before the eighth walk along the garland of lights, we see that the dwarf will never act on the lights 1, 2, 3, 4, 5, 6, 7, which means that the state of the light bulb number 7 can be carried down all the way to the end of the experiment safely, like so. And during the 8th walk along, the dwarf in our setup will only act on the light bulb number 8. It will flip the state of that light bulb to its opposite, like so. And that means that the remaining light bulbs that in our experiment the dwarf did not act on can be percolated down as is, like so. Before the 9th walk along begins, we also realize that the dwarf will never act on the light bulbs numbered 1 through 8, which means that the state of the 8th light bulb can be carried down all the way to the end of the experiment safely, like so. And during the 9th walk along, the dwarf will change the state of the light bulb number 9 from off to on, like so. And we carry down the state of the light bulb number 10 because the dwarf did not act on it in this walk along. Consequently, during the 10th and the last walk along in our experiment, the dwarf will not act on the light bulbs numbered 1, 2, 3, 4, 5, 6, 7, 8, 9. That means that the state of the light bulb number 9 can be brought down to the end of the experiment safely, like so. And in this walk along, the state of the light bulb number 10 is on. The dwarf will flip it to the opposite state, meaning it will turn it off. And this concludes our experiment. We see that the light bulbs number, let me use the white color just in case, 1, 4, and 9 are turned on, and the remaining light bulbs are turned off. Now, what kind of conclusion or what kind of observation can we make from the result of this experiment? And this, by the way, may sound a little technical, but the way things work in mathematics is that whatever the result of a particular mathematical experiment we witness, that result must sit on the receiving end of some mathematical machinery or of some vaguely defined mathematical layer. Whether we have the intellectual capacity or the current knowledge to identify that mathematical layer is a different story, but on the receiving end of the result of this experiment, a particular layer of mathematics does sit, in the words of your master. Now, in order to see how the reinterpret and conquer problem-solving approach can be applied to the results of this experiment, let us, for example, count how many times did the dwarf act on the light bulbs that are numbered with, let's say, prime numbers, because prime numbers are always good candidates to look at. Let's see. The light bulb number 2 was acted on only twice. We'll write 2 over here. The light bulb number 3 was acted on only twice as well, during the first walk along and the third walk along. The light bulb number 2 was acted on twice during the first and the second walk alongs. The light bulb number 5 was acted on how many times? Also twice, during the first walk along and during the 5th walk along. The light bulb number 7 was acted on also only twice, write 2 over here, during the first walk along and the 7th walk along. Now, in the context of prime numbers, how does 2 come into play? Well, it should be fairly evident that a positive whole number greater than 1 is prime if and only if it has exactly and precisely 2 positive divisors, the number 1 and that prime and that number itself. So the moment the words positive divisors enter our vocabulary, we now think, aha, we're probably onto something. For more experimentation, Let us see, for example, the number with a large number of positive divisors, like 6. How many times this light bulb number 6 was acted on? Well, the first time it was acted on during the first walk along. The second time it was acted on during the second walk along. The third time it was acted on during the third walk along. And the sixth and the final time it was acted on during the sixth walk along. Consequently, we now think, what does 6 and 4 have to do with each other in this context when we already uttered the words positive divisors? Well, it is a straightforward fact to know that the number 6 has exactly 4 positive divisors. 1, 2, 3, and the number 6 itself. So now we may generate a hypothesis that this problem is actually not about our friendly dwarf walking along and flipping lights on and off, annoying the neighbors who probably think, here goes the neighborhood. But this problem is actually reinterpreted or reinterpretation of a certain elementary number theoretic fact or some number theoretic situation. We also see that perhaps a very easy or a very straightforward pattern that we uncover in the result of this experiment is the fact that the light bulbs that are on are all represented by perfect squares. In other words, 1 square is 1, 2 square is 4, 3 square is 9. So what is going on here? Why perfect squares represent the lights that are on and not perfect squares represent the light bulbs that are off? At this point, we may recall or we may deduce the elementary number theoretic fact that if a positive whole number is a perfect square, then it has an odd number of positive divisors, and if a whole positive number is not a perfect square, then it has an even number of positive divisors. Back in my time, where all the examinations were performed in a verbal face-to-face real-time interrogation by the math or by the theoretical physics professor, that would have been a perfect verbal examination question. Can you explain why, or can you generate a convincing story or a convincing line of reasoning why, if a number is a perfect square, then it must have an odd number of positive divisors, and why a number that is not a perfect square must have an even number of positive divisors? Well, there are several ways to deduce that fact, and here we will use slightly more formal approach and we'll obtain an interesting result in the end as follows. First, let us concentrate on a pair of p being a prime number raised to a non-negative integral power a. For example, let's say 5 raised to the power of 3, for example. So here, prime p is represented by 5, and a non-negative integral power a is represented by 3. What can be said about the number of positive divisors generated by this dynamic duo? Well, the power 0 that comes out to 1, will that be a positive divisor of p raised to the power of a? The answer is yes, sure. We remember that an integer a divides an integer b if there exists an integer c such that a times c generates precisely b. And in this case, our original number, p to the power of a, can be represented as p to the power of 0 times
p to the power a minus 0, which is p0 plus a minus 0. These guys are zeros, equals to p to the power of a.
So that is precisely the representation of the fact that p to the power of 0 divides the number p to the power of a. So we chalk up 1 to the total number of positive divisors. Will p raised to the first power be a divisor of p to the power of a? Yes, of course, because again, we can represent p to the power of a as p times p to the power a minus 1. And that can be represented as p to the power 1 plus a minus 1, p to the power of a, which is again a representation of the definition of one integer dividing the other.
What about p squared?
Will p squared generate a divisor, a positive divisor of the number p raised to the power of a? The answer is yes, of course. Again,
we can represent p to the power of a as p squared times p a minus 2, which is p to the power of 2 plus a minus 2, which is again p to the power of a.
And this is a representation of the fact that one integer, p squared, divides the number pa, and so on. It should be evident that
for as long as, let's say, our integer k varies between a and 0, the number p to the power of k divides p to the power of a.
Which means that our dynamic duo, p to the power of a,
generates a plus 1 positive divisors of p to the power of a.
Now we recall the so-called FTA, or the fundamental theorem of arithmetic, according to which a whole positive number greater than 1 is either prime already, or can be represented as a product of primes in a unique way if the order of the set prime factors in this representation is ignored. In other words,
a whole positive number n greater than 1 can be represented as, let's say, p1 raised to the power a1 times p2 raised to the power a2 times, and so on, p sub k raised to the power ak times, and so on, let's say pm raised to the power am.
Now we just showed that one specific pair of a prime p sub k, let's say, raised to the power a sub k, generates
a plus 1 or that many positive divisor
of a number n. Now let's think about it. Is the specific choice
of a divisor of the number n for, let's say, prime p1 and the power a1
affects the number of divisors generated by the remaining
primes in that number?
Well, the answer to that question is no, because again,
the number n in this case can be represented which way? Let's say we decided to go with p1 squared. Then the rest of the number can be still represented as p1 raised to the power a1 minus 2 plus the rest
of the guys, which precisely represents the fact that p squared sub 1, for example, is a divisor of a number n. But that means that the number of divisors, the number of positive divisors of a number n generated by any specific pair of a prime and its exponent, is independent from the number of positive divisors generated by the remaining pairs of primes and their exponents. That means that we do not have to apply more nuanced or more complicated counting principles, such as
inclusion-exclusion principle, and the good old multiplication counting principle applies. According to that principle, we can write down actually the formula tau n. In my time that was called tau n, that comes, if I'm not mistaken, from the German word for divisor, will be equal to the number of positive divisors generated by the first pair P1A1 times the number of positive divisors generated by the second pair A2 plus 1 times, and so on, times the number of divisors generated by the kth prime A sub k plus 1 times, and so on, times the number of divisors generated by the last prime in this prime portrait of a whole number n. But now, how does this formula help us answer the question of what is going on with the number of positive divisors of a perfect square? Let us think about it. If a number is a perfect square, let's say, we will say x square equals this, let's say, for the sake of the argument. That means that the whole number, the whole prime factorization of the number is raised to the second power. And that means that this representation of a perfect square can be modified slightly when we move 2 into every power of the corresponding prime, which is a fact that we should remember from middle school days, where we learned that, for example, AB square equals A square B square. Now, that means that if a number is a perfect square, then the exponent of each and every prime in the factorization of that number is a number that is what? Is a number that is even, because it's represented as 2 times A1, 2 times A2, and so on. But that means that in the formula for the number of positive divisors of a perfect square, each term in that product will be represented as 2A1, let's say we'll call it tau of x squared, 2A2, 2A sub k, and 2A sub 1. Now, but what do these numbers now represent? 2A1 plus 1, 2A2 plus 1, and so on. Well, each and every factor in this representation of the total number of the positive divisors of a perfect square is a museum quality representative of a number that is odd. And more than 2,000 years ago, in his book Elements, Euclid proved, if I'm not mistaken, that was book 9, proposition 27 or 29, I'm not sure, that a product of two odd integers is an integer that is odd itself. Consequently, if our perfect square represented by only one factor, that factor will be prime already. It will be odd already. And if that number is represented by two factors, then a product of an odd number times an odd number will also be odd. And regardless of how many factors in this chain we have, we will be able to roll up that product of odd integers into an even integer that is essentially odd. And that specifically demonstrates the fact that if a positive whole number, a perfect square, then the total number of positive divisors of such a number must be odd. However, let us now analyze what is going on with whole positive numbers that are not perfect squares. What does that mean? Well, if a number is not a perfect square,
then that means that at least one power of at least one prime must be a number that is not even or a number that is odd. And if such a number is odd, let's say a sub k, then it should be representable as, let's say, 2 alpha k plus 1. Now, what does that mean? That means that when we put this exponent back into the formula for the total number of positive divisors of a number that is not a perfect square, then that particular factor will look like 2 alpha k plus 1 plus 1, which looks like 2 alpha k plus 2, which looks like 2 times alpha k plus 1, and that number is already even. And no matter how many factors in this finite product will be odd, that single presence of 2 will make the entire product an integer that is even. Consequently, if a number is not a perfect square, then the number of positive divisors of such a number will be even. Now that we understood where our ideas and where our hunches are coming from, let us go back to the original problem. Here we can represent this whole situation, or we can model what is going on with the states of light with the -1 arithmetic. When -1 is raised to an odd power, then what will the result of such a construct be? Well, in this case, we can represent this as -1 to the power 2k times -1, and this can be represented as -1 squared raised to the power k times -1. This will be 1 raised to the power k times -1, and this will be precisely -1. If, on the other hand, that number -1 is raised to an even power, let's say represented as 2k, then what will happen? Then that number can be represented as -2 squared raised to the power of k. This will be 1 raised to the power of k, and that will be 1. And by the way, the reason I spelled out this seemingly obvious manipulations over here that way is because you will see these manipulations again in the theory of groups course, specifically when you will be dealing with the so-called generators and defining relations. Now, with the negative number on, we associate the state, the initial state of each light bulb, and that will be, let me use the yellow color over here, that will be on. And what is the final state of this manipulation? Is -1 or on again, on. And over here in this experiment, if -1 is raised to a positive power, the initial state is on, but what is the final state? The final state is off. We'll mark it with the blue color, off. Consequently, because during this walk-alongs, our dwarf only flips or changes the state of every light to its opposite, this model of raising -1 to a odd and even powers applies. And what do we see over here? Well, what we see over here is that if a number of a light bulb on which the dwarf acts is not a perfect square, the dwarf will act on it precisely how many times? An even number of times. It means that the initial state of this light bulb will not be preserved, and it will be changed to the state off. In contrast, if the dwarf applies his actions to the light bulbs that are numbered with perfect squares, 1, 4, 9, 16, and so on, then because these particular numbers have an odd number of positive divisors, then the arithmetic of -1 raised to an odd power applies, and that arithmetic preserves the initial state of the light bulb, and this particular light bulb will be on. Consequently, here, let me use maybe the red light. The answer to this question will be the light bulbs that are, let me erase this, the light bulbs that are numbered with perfect squares, which are 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100 will be precisely on, and the light and the remaining light bulbs will be off. In other words, what we see here is that according to the Reinterpret and Conquer problem solving approach, the process of the dwarf walking along the garland of lights and flipping the state of every corresponding light bulb to its opposite can be modeled with the process of probing or enumerating the next positive divisor of a given whole positive number, and the problem is solved. In the best of traditions of practicing mathematics correctly, let us reflect on our problem-solving experience. In this specific problem, we realize that through the application of the Reinterpret and Conquer problem-solving approach, we can step away from the language of the dwarf walking along the garland of lights and changing the states of these lights to its opposite, to the language of probing the next positive divisor of a corresponding whole positive number. From that observation, or from that idea, we deduced the formula for the total number of positive divisors of a given whole positive number based on its prime factorization shown over here. From that formula, we proved that if a whole positive number is a perfect square, then the number of positive divisors of that number must necessarily be odd. And if a whole positive number is not a perfect square, then the number of positive divisors of such a number must necessarily be even. We then realized that the number of times that a particular light bulb will be acted on by the dwarf is equal precisely to the number of positive divisors of the corresponding number that is attached to this or that light bulb. And then through the application of the arithmetic of -1 raised to the odd or to the even power, we realize that at the end of the 100th walkthrough, only the light bulbs that are numbered with perfect squares, 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100 will be turned on and will shine brightly, and all the remaining light bulbs whose numbers are not perfect square will be turned off. From this experience, just like from the experience of solving the previous problem, we realize that essentially each and every worthy or interesting mathematical problem is a package that consists of two parts. One part is the material that does not vary and represents the technical essence of this problem, and the other part is something or the material that is irrelevant minutia in this case, and the material whose variance precisely does not affect the technical essence of the problem at hand. In this specific problem, what was the technical essence of the problem that does not change, and what was the irrelevant minutia? Based on the solution that we just demonstrated, it should be evident that the technical essence of this specific problem is the number theoretic fact that the number of positive divisors of every perfect square must necessarily be odd, while the number of positive divisors of a number that is not a perfect square must necessarily be even. And from here, it follows that the very language of our friendly dwarf walking along the garland of lights and changing the state of every corresponding light bulb to its opposite represents the irrelevant minutia, or something that can change, and that change will not affect the essence of the corresponding number theoretic fact. Also recall that in Season 1, Episode 1, when we gave several definitions of mathematics, we also enumerated some basic properties of mathematics. And one of these properties was the fact that each and every mathematically established result is completely and totally detached from time. In other words, no single mathematically established result has an expiration date attached to it. Consequently, the very basic number theoretic fact that we established in this particular solution was true 5 billion years ago, it is true now, and it will remain true 5, 7, 10 billion years from now. And as a demonstration of the fact that every worthy and interesting mathematical problem is a package of two things, as I explained over here, in the list over here I came up with several possible other or alternative formulations of the problem that we just solved. For example, let's say we're given 100 wooden boards, and these boards are painted, let's say, all white. And on the kth walk along, we repaint the kth board in the opposite color. If that board was painted white, we color it in black, and if it was colored in black, we paint it in white. And the question is, by the end of the 100th walk along or repainting session, which boards will be painted white? As another option, let's say we line up 100 people, single file, and we open the eyes of all these 100 people. And again, on the kth walk along the single file 100 people, we change the state of every kth person of the eyes of that person to the opposite. If the kth person has their eyes open, we close them, and if the kth person has their eyes closed, we open them. Consequently, the question is, at the end of the 100th walk through the single file of these 100 people, which specific people will have their eyes open? Also, let's say we let 100 trumpets take international middle A, which corresponds to 440 hertz. Let's say they play middle A every second or some such. Then on the kth walk along, we tell to the kth trumpet, if you are playing the international middle A, don't, and if you do not play, start playing. The question is, at the end of the 100th walk along, which trumpets will be playing the international middle A? And right now, it should be evident that every other formulation follows the same pattern. For example, we can put 100 coins, put them on a table heads up, and on the kth walk along, we flip the coin to the opposite side, which coins will be heads up at the end of the 100th walk along. We can raise 100 flags and then flip the state of the kth flag during the kth walk along to the opposite. If the flag was raised, we'll lower it, and if the flag was lowered, we raise it. The question is, at the end of the 100th walk along, which flags will be raised? Fill 100 glasses with water and then empty or fill them up with water. Which glasses will be filled with water? Distribute 100 prisoners across 100 cells, one prisoner per cell, and then walk a prisoner out of the cell or walk the prisoner back into the cell. You already understand the drill, which prisoners will be, let's say, in the cells by the end of the 100th walk through. Put 100 gold coins into 100 jewelry boxes, one gold coin per box, and on the kth walk along, either take the gold coin out of the jewelry box or put the gold coin back into the jewelry box. Question is, by the end of the 100th walk along, which jewelry boxes will have precisely one gold coin in them, and so on. Pretty much by design, if you're watching this channel, you are a smart individual, and as such you should be able to, and this is our informal suggestion, that it's a good idea to go through this exercise in which you on your own generate a problem statement that wraps the technical essence of this particular problem shown over here into your own language, where instead of wooden boards, eyes of the people, trumpets, coins, flags, glasses of water, prisoners, or jewelry coins, you use your own vocabulary, and by doing so, hopefully, this will help you develop your better understanding of mathematics. Meanwhile, we'll move on to the next challenge. If you are new to our channel, then as a matter of naming convention, we designate the mathematical problems with the letter M like so. For example, the string S1M10 designates the mathematics problem number 10, which we solved during the season number 1. The problems in physics we designate with the letter P as shown over here in a similar manner. And the problems in computer science we designate with the letters CS in the similar manner as shown over here. Consequently, in the next problem, S1M10, the challenge is to find an alternative expression for the following finite sum. The finite sum of squares of the trigonometric function of cotangent of a patterned argument, which looks like the product of the positive integer k and pi over 11, with the variable k changing from 1 to 5. From the solutions of the previous two problems, we know that pretty much every interesting and every worthy mathematical problem comes in as a package of two things. The things, or the material that does not vary and thus constitutes the technical essence of the problem at hand, and the material or the things that do vary, but the very variance of this specific material does not affect the technical essence of the problem at hand and thus constitutes the irrelevant minutia. Consequently, when we take on a mathematical problem, we should strive to develop the skill or develop the ability to separate what does not change or constitutes the essence, the technical essence of the problem, from what can and does vary without affecting the technical essence of the problem at hand. And thus we should concentrate our effort on addressing or fighting the fight, so to speak, with the things that matter and ignore the things that do not matter. Because right now we're studying the mechanics of the reinterpret and conquer problem solving approach, it is evident that one way in which this particular problem can be solved is precisely through the application of the reinterpret and conquer problem solving approach, which means that one way to solve this problem correctly is to look for a subtle or for a nuanced reinterpretation of the local subject matter. This is it for this episode. Thank you very much for watching. Thank you for staying with us. I'll see you in the next episode, in which I will discuss the solution of the problem S1M10.